require expansion. And another thing is that is taking place up to the certain x, and after that you can say that beyond a certain value x, in the region you can say 0 less than equal to x is less than equal to L. In this region there is a position xx. We have taken this as a point in that region xs. There is no sliding. No sliding taking place between workpiece between the workpiece and the dies. And also another fact is that due to the increasing frictional stress which reaches the maximum value shear yield stress, the frictional this one is a frictional stress, that is a tau we have taken. This is equal to our shear yield stress at this position. So, what we have? We have at x is equal to xx and rest zone is Sx is less than equal to x is less than equal to L. So, finally, here we have a material that is the deformed one. From here to here, this point is say as x is there. So, before this we have a sliding one, and after that there is another zone, that is a sticking zone. Here it is a 0 and here the length is L. So, first of all, whatever we have taken s is equal to x means 0 less than equal to s and less than equal to Sx. For this one is happening, and rest amount where the sticking is taking place, that is meant for the another zone. Now, again in that case, when we have defined the two zones, So 0 less than or equal to our x is less than or equal to our Sx, you can say. This one is meant for the sliding zone, and here we are using tau is equal to mu and whatever be the force is applied from the top. For the another reason, Sx, that is less than equal to our variable x and less than equal to the length L. Here we have to take the stress is equal to our shear yield stress. So now we have to consider all this one. Up to now we have taken the two zones, means two zones are, first one is a sliding one, another one is a sticking one. For the first already we have seen that is 0, x and x axis there. So total our analysis has been divided into the two part. First one, that is a sliding one, another one is for the sticking one. For the sliding one, we are taking whatever be the force is applied from the top into coefficient of a friction, and for the sliding zone, that is meant from whatever the dividing point is there, x is there up to the middle one, that is a sticking zone. So we have a two zones. Earlier we have taken our platen or the work platen under which our workpiece has been deformed, and deformation we have taken the two zones. First one already you are observing it here, that the first one is this one and second one is here. Now we will discuss one by one for the sliding zone. So for the sliding zone, means here non-sticking zone we are saying as non-sticking. We have to use tau is equal to coefficient of a friction and the force. Now just put this value in our earlier expression, that dP is equal to 2 tau upon h into dx. So finally what we have a dP is equal to twice mu P by h into dx. If we integrate it, now rearrange it, if we are rearranging it, finally we have dP by P, this is equal to nothing but twice mu by h if we are integrating it. So here it would be a dx. For integration constant C1 will come into our picture. This one is meant for that 0 is less than equal to our x variable, the distance, and between a point from where the sticking zone start, that is a x-axis. Or finally we have an expression that so this one is expression. Now we have to take the limiting points, means at x is equal to 0, sigma x is also equal to 0. So in that case we can say that, and another one is that whatever the peaks are there, we can say p plus sigma x is equal to 2k. So the p is equal to 2k. P is equal to 2k. Therefore, we can write that C1 is equal to log of 2k. So here we have the value of C1. In this way, if we will put the value of a C1, so our P, this P will become twice k e to the power twice mu x by h. Again, it should be noticed that this one is meant only for 0 is less than or equal to x is less than equal to our xs. So this one is a one important formula or expression that is before the sticking zone. Another one for the sticking zone, now we have to consider for the sticking zone. For the sticking zone, what we are using, tau is equal to the k, and putting this value, substituting this value in the same expression, that is a dp is equal to twice tau by h into the dx. So finally we have dp is equal to twice k by h dx. Now integrating it again, we have dp that is equal to twice k by h dx plus C2, and this one is in between Sx less than equal to whatever the variable x is varying, in between this L. So finally our P will be that is equal to twice k into x by h plus C2. Also, our P is equal to the PS at S is equal to XS. Then this C2 will be equal to our P2 minus twice Kx by H. So, if we'll put the value of a C2 in earlier expression, so the finally we have P minus PS. This would be equal to nothing but twice K by H X minus XS. So, this one is another important expression, or you can say as a 2. So, according to the first, PS that was equal to twice K exponential of twice mu XS upon H, or finally we have the value of P that is equal to twice K